derivation of Planck units, and creation of black hole. So the first thing to look at is the idea of squeezing two electrons together in a small space. So if we have two electrons and you try to squeeze them together in a small space, and these two electrons are at a distance r, there are two situations we can come out from this behavior. The first one is to look at the gravitational force that's applied between the two electrons as you try to squeeze them in a small space, and the Coulomb's force, which is the electrostatic force, and for the gravitational force, which is Newton's gravitational force, and this one is Coulomb's, and the Newton one is that the big G times m1 m2 over r squared, and for the Coulomb's law is equal to q1, q is the charge, q2 over 4 pi epsilon naught r squared. What we can do is to find the ratio between these two forces to see which one is bigger and which one is weaker. The mass is the same because it's mass of electrons, and the charge are the same because it's charge of electron. And so we can rewrite this formula as big G m squared over r squared, and this will be the charge is electron, so it's going to be E squared over 4 pi epsilon naught r squared. The two r squared will cancel out. This is inverse squared law, and so this is F big G and F E. The ratio between the two forces, F E over F big G, will be, well, that cancels out. So we're going to have this on top. Let's put E squared over 4 pi epsilon naught r squared, and we're dividing it by this one here. And when you divide, it becomes times, and then you flip it. Well, let me just put it there. So that would be big G m squared over r squared, and that ratio will become E squared over 4 pi epsilon naught r squared times r squared over big G m squared. As you can see here, the r squared will cancel out. The ratio Fe, the Coulomb's force over the Newton's gravitational force, will be, well, E squared over 4 pi epsilon naught big G m squared. What we can do is plug these values in, but I'm going to use a calculator to do that, so that'll be quicker. So with the calculator, I'm going to plug that in, so obviously turn that on, and then I'm going to, because it's a fraction, so I'm going to put a fraction key there, and I need the E squared. I can get that because I go to the shift constant 7 here. I need a universal constant, so, and the E value, actually the E value is not here, so I can go back to I could look at the atomic nuclear, so number 3 actually. And do I see the E value there, the charge? E value is not there. Let's go back again. I'll try number 2. Yes, E value is 3, so press 3 there. I squared it, bring the arrow key down. I want to put 4 times shift the pi times, I need the epsilon naught. Okay, so let's go back to the shift constant. Where would epsilon naught be? Try number 1. There we go. And epsilon naught is number 4. So I'll put 4 there. So this is how to do it using the calculator. And then times the value for G, which will be shift constant again, universal constant, 1. G is number 7, so I'll put 7 there. And then I want the mass of electron. We know that's 9.11 times 10 to the power minus 31 kilogram, but we can't put it in there using the constant and the mass of electron. I think let's try 3. Mass of electron is number 3 there, so I'll put 3 there. I want to square it, and if I press equal sign, so the value I get here will be 4.166 times 10 to the power 42. It's a ratio, there's no unit, these are both forces. So what that meant is that the electrostatic force, Fe, or the Coulomb's force, is far greater than the gravitational force. The Coulomb's force is more effective here because of the size and the range. The gravitational force is an attractive force, but the Coulomb's force in this case is a repulsive force. So that's more effective than the gravitational force with that range. This is classical physics. That's what we're looking at here, classical physics. We're applying classical physics to these tiny particles in a small range. And because the range we're looking at here, the size of an atom is about, so if you have an atom, the diameter of an atom is about 10 to the power minus 10 meters. And in nucleus of an atom, the nucleus of an atom diameter, and that's about 10 to the power minus 15 meters. That's femtometers. And in this case, the gravitational force is not that effective. But this confinement that we're looking at, we need to now introduce something called the quantum physics. And so this is why we introduce the quantum physics. As we squeeze these two electrons together, what would happen? The classical physics will start to misbehave. And so let's just say introducing quantum physics. Introducing quantum physics or quantum mechanics. For obviously this is for a small particle, and this is where things get exciting. The first person, well, Carl Heisenberg was the amazing gentleman who introduced the idea of uncertainty principle. He was born in 1901, just after Max Planck introduced Planck constant in 1900. He died in 1976. You may have heard the saying that Heisenberg may have been here. He published his uncertainty principle in Copenhagen in 1927. And Heisenberg, here he developed the uncertainty, or he published the uncertainty principle, where he says that the position of a particle, we cannot know the position of a particle at the same time as knowing the momentum of a particle. And that there's a relationship between the two, which is the position is x here and momentum is p. Momentum is mass times velocity. And that is greater or equal to h bar. H bar is reduced Planck constant over 2. Sometimes this is written as changing position, changing momentum, or uncertainty in position, uncertainty in momentum, greater or equal to h over 4 pi. Sometimes you may see it written like that or like this. So we're going to apply the uncertainty principle to this situation because we've applied the quantum classical physics and we realize that this is what we're getting. And so h is the Planck constant. H is Planck constant, and which I said was introduced in 1900 as a form of E equals hf. That means energy is equal to Planck constant times the frequency. H bar is equal to h over 2 pi. So this is called reduced Planck constant. So what we're going to do is apply the quantum principle of uncertainty, which we said that the position times the uncertainty momentum is greater or equal to h bar over 2, but we can ignore the 2 because 2 is just a number. And so what we can do is divide both sides by the position. So delta p greater or equal to h bar over delta x, where delta x is the r, the distance between the two electrons we're squeezing together. So we can say delta p is greater or equal to h bar over r. We know that delta x is equal to r, and so I can convert these changing momentum to energy by multiplying both sides by c. C is the speed of light in vacuum. So delta p c is greater or equal to h bar c over r. And momentum times speed is energy. If you check the unit, you have the same unit as energy. So therefore, delta E is greater or equal to h bar c over r. So what this means that is that as the energy increases, when we're squeezing the two electrons to a small distance, which is decreasing. R is decreasing, the energy is increasing. As R decreases, energy increases because it's inversely related. The mass will begin to increase according to the Einstein's special theory of relativity, which states that E is equal to mc squared. So as energy increases, mass will increase in a small confinement. What we're looking for is how do we make the ratio of Fe over F big G to be approximately equal to 1. Well, we can do that by equating the E squared over 4 pi epsilon naught. There's the permittivity of free space, G m squared, to be equal to 1. And if we do that, making m squared the subject, m squared will be equal to, just take that one over there, and then you get E squared over 4 pi epsilon naught big G. And we square root both sides, and so m will be square root E squared over 4 pi epsilon naught big G. So this is the mass, and this mass that we get, we can then put it into the energy. E equals mc squared, and that energy is now going to be transferred onto the energy here to give us the relationship for the uncertainty quantum principle. And so what we can do now is to take the energy E, which is greater or equal to h bar c over r, which is that one, and make r the subject. So r should be less or equal to h bar c over e, because we're still squeezing it to a smaller distance. So the distance is equal to that value, or should be decreasing. And if we plug in this value at this point in time, let's rewrite E, because we know it's less or equal to h bar c over mc. That's E is mc squared. So R will be less or equal to h bar over mc. And if we, at this point, if we use the mass of electron here to calculate this, we should get R to be approximately equal to 3.8 times 10 to the power minus 13 meters. As I said, this is, if you look at the size, this is the radius here. If you look at the size of an atom, the diameter is 10 to the power minus 10 meters. So this is smaller than that. And if you look at the nucleus of an atom, the diameter of a nucleus is 10 to the power minus 15 meters. So this is smaller than that. So it's in between those two. So we're getting it smaller. How do we find this value? Well, again, use your calculator and use the constant provided by your calculator to find it, because that's a constant, and that's a constant. We switch it on and we go to ratio, fraction key here, because h bar is in top, so go to shift constant, because that's a constant value there. Universal constant is 1. I need h bar, which is number 2, so number 2 there, so I put 2. Bring the arrow key down. I need a mass of an electron. Well, so I can go to shift constant. Where would mass of an electron be? Or perhaps I was thinking it'd be number 3. That's why I went there before. Yeah, so mass of an electron is number 3 there. If I put that in there, I want to times it by the speed of light. That's the speed of light is a constant universal constant, sorry. So I go to shift constant. Number 1, the speed of light is CO, the speed of light in vacuum, and so number 3 is just speed of light. So we get 3.86, I'll put 6 there, times 10 to the power minus 13 meters. So roughly that's the distance. But we want to continue to squeeze it beyond that distance, beyond that confinement. We want to continue to squeeze this electron in there. So that's what we're doing. We're just squeezing electron into small space, and then we're working out what's happening. And as R gets smaller, that's what we're doing, we're making it smaller, then the delta X decreases, which means that the delta E energy will continue to increase. Therefore, the mass will start to create mass of electron, and the gravitational big force will begin to have an impact because the mass is increasing. So the gravitational force will begin to have an impact. And because the mass is increasing and gravitational force is becoming more important, we would like to see the Fe over F big G roughly equal to 1. So when will that happen? Because this will start to increase and therefore the ratio will begin to decrease. Before the ratio was massive, it was about 10 to power 42. Now we want that to, as this increases, the ratio will continue to decrease. When will it get to ratio 1? As we said, we obviously set this is where it gets to ratio 1 and we do this. Obviously we knew that delta E, as we said earlier, is greater or equal to hc over r. Applying the uncertainty principle here, this is quantum physics, where we said r will be less or equal to hc over h bar c over delta E, and we said that r is less or equal to h bar c over mc squared, and that r is less or equal to h bar, this reduced Planck constant, over mc, and that is expected roughly to be about 10 to power minus 35 meters. So this is where the distance will be, because we put that in that distance in there, that's what we get, which means that at that distance we will create a black hole, because the mass will get so big, will get condensed in that little space, that it will then turn into a black hole. But in order to find exactly this mass, this distance, what we've done is we've looked at an object escaping a gravitational force. If you have a mass object, a mass m of an object escaping a gravitational pull of a bigger mass, we know that the work needed to be done to pull the object from the mass. So the work needed to be done is the energy, which is force times distance. We know the force is big G, big M, little m over r squared, the Newton's gravitational force, times the distance r, and that will be big G m r, because the r cancels r. So this is, you can get this from integration. When you integrate this, you do w equals to f dr, and you move the object from r to infinity. This is how we get that r. So that's through integration. And then now the kinetic energy required to translate the object into a higher speed to escape the gravitational pull will be a half mv squared. So we're saying that, and the object in a gravity of a small m and big M, we want to escape that from that big M. It has to have a velocity, and the velocity will have a kinetic energy. And so that's kinetic energy. That kinetic energy must be equal to the energy of the gravitational pull. So G M over R. And now we need to calculate the speed for that. And the speed, the velocity, will then be v squared equals to, well, by the way, this one is little m as well, and little m, because it's only r that we cancel, not m. So we have the m here, we cancel that m, and then you're going to have v squared equals to 2gm over r, and therefore v will be the square root of 2 gravitational constant m over r. So that will be the escaped velocity. But what's happening here is that as the mass increases, the escape velocity will also increase, and as the radius gets smaller, which is what we're trying to do when we're confining the object into smaller distance, as the radius gets smaller, the escape velocity also will be greater. So what about a more dense object? Very, very dense object. That means it's going to have a big escape velocity. If we look at the escape velocity for object on Earth, it's about 11.19 kilometer per second. For Jupiter, it will be about 59.7 kilometers per second. For Mars, it's about 5.03 kilometers per second. And for Venus, it's about 10.36 kilometers per second. But if we're looking at a very dense object, and that it's very difficult for any object to escape it, even the light. So if we need the speed of light to escape it, and even light couldn't escape that object because it's so dense, and then that object would be a black hole, because nothing comes out of that. I mean, light can't even come out of it, hence why it's called black hole. So if you need the speed of light to escape this dense object, so we change v to c as the speed of light. And what we can do now is to rearrange this equation to make r this object. So that will be the distance. So that distance, r, we call it r subscript s, will be equal to, if you square that, you have to square this. So that will be c squared, yeah? Because if you squared that, so you want to just swap this c squared here. So the r will be square root of, well, let's just write this properly actually, because I'm making a big mess here. So the r will be 2gm over c squared, because I square that, I have to square that, and that square root will disappear, and we just swap this together. So the r, and that r has a name for that, where the speed of light is used as the escape velocity. We call that r, which is rs, as that's W-A-R, Schwarzschild radius. So that's a Schwarzschild radius, because it's the radius that is required in this equation when the escape velocity is speed of light. And so we can work out what that radius is. So in order to find the radius, we write down the Schwarzschild radius, which is 2 big G m over c squared. And this is from gravity effect. And we can also write r, which is the h bar over mc, and that's from quantum, so that's from gravity, and this is from the uncertainty principle, which is quantum. And if we compare the two together, we could find the radius that we need, and also we can find the mass as well. So let's find the radius first for these two. In order to find the radius, we need to eliminate the mass. So find the radius. So to find the radius, what we need to do is, we're making m the subject here. Make m the subject and substitute into the other one. So we could say that these two are the same, and make m the subject here, or there, it doesn't matter. So look at this one for quantum. So r is equal to h bar over mc, and m will be h bar over rc. And if I take that, I can put it into the rs for the gravity, where r is equal to 2gm over c squared. So I need to replace m with that. So that will be equal to, well, let's ignore the 2 because 2 is just a number. So that will be equal to g over c squared times the m, which is h bar over rc. So that's m here. I'm just replacing it with this one here. I've ignored the 2 because it's just a number, and therefore it's a small number too. So r is equal to the big G h bar over rc cube, because c squared times c, and there's an r here. So now I'm going to times that r to that, so that r goes to there, so you get r squared is h bar big G over c cube, which means the r will become root of h bar big G over c cube. And this r is called the length. We call it Planck length, which is this value here. So this is a length that we can squeeze the object into, where a black hole will form, because the mass will be too big. It will become condensed. It will become so dense that it will form a black hole. And this is this length here. And this length is called Planck length, because he's the first person to think about it, Max Planck. And we can work out that length to tell us what it is. So that length is going to be, using my calculator here again, we go to universal constant here, h Planck, big G, and speed of light in vacuum. So if I turn that on, I need a square and fraction key there. And then I'm going to find the h bar, shift, constant, universal constant. H bar is number 2, so I press 2. I'll times that by the big G, shift, constant, universal constant number 1. Big G is number 7. Bring the arrow key down. I want the speed of light in vacuum, shift constant number 1. Number 3 is the speed of light in vacuum, press 3. But I want to cube it, is to power 3. So I need to press that, and I can enter the 3 qubit. And I need to press equals. So now the Planck length is 1.616 times, well, you can carry on, so times 10 to power minus 35 meters. So that is the length that we can squeeze this object into to then start to form a black hole. Now we know the Planck length. We could find the Planck time and Planck mass. So the mass for that object will be, we can use the same substitution here, but this time we eliminate the radius and we make m the subject. We can find the Planck mass. So let's do that. Find the Planck mass. So we said find the mass. And the mass here is the Planck mass. So this is Planck mass. That was Planck length. So for Planck mass, I want to eliminate, well, we already know it anyway because we know m here is that. So I know the Planck length. I can actually substitute it here, or I could just eliminate these two here to find the Planck mass. So I need to eliminate the radius here. So equate these two together. But remember, you have to forget that too. So just equate these two together, make m the subject. So let's do that. So we go g m over c squared must be equal to h bar m. Well, let's assume these are the same masses. So over c and multiply them together. You get m squared equals to, well, make the c squared goes there. So that's h bar c squared, big G down over big G c. Well, one of them we cancel each other, right? So that implies we get m squared equals to h bar c over big G. So if we square root both sides, m will be root h bar c over big G. And that is the mass. That's called Planck mass. So that will be the mass. And we could actually work it out again and find out what value is that mass. So we get our calculator here again. But this time we want the c and the big G. So let's start afresh. Square root. And we want fraction p. We want h bar, the reduced Planck constant. So we shift and press 7. Universal constant is 1. H bar is 2. And then we want to times it by the speed of light in vacuum. Again, shift universal constant, which is 1. Speed of light is 3 there. And bring the arrow key down and find big G. So shift universal constant 1 and 7. So that's that. We press equals. Right. So the mass will be equal to 2.18 times 10 to power minus 8 kilogram, which is roughly equal to 22 microgram of the object. So that'll be the mass, and this mass is called the Planck mass. Now, we know the Planck mass. We know the Planck length. The next thing to calculate would be Planck time. So let's find the Planck time. Alright, Planck time. Okay, for the Planck time, let's just write that down here. Planck time. We know that, let's use capital T for Planck time here. And time is the distance traveled, which is Planck length, over speed. Speed is the speed of light. So time is distance traveled over speed. We can write it as, so we can write speed equals to distance over time, and therefore time is distance over speed. But the Planck time will be the distance, which is Planck length, over the speed, which is speed of light. We know what Planck length is, so our P is the root we just calculated, which is h bar big G over c cube. And so what we're going to do now is put it there. So Planck time will be LP times 1 over C. I'll just split that up in a way I can then insert this one over there. So that will be root H bar big G over C cube times 1 over C. Well, I need to incorporate that into there. I need to put this into there. In order to do that, I need to change this. So root H bar G over C cube times root 1 over root 1 squared over root c squared. Root of c squared is c. Root of 1 squared is 1. In fact, the whole thing here is 1. So, but because they're all roots, I can put it in. Therefore, that will be root h bar times big G times 1 over c cube times c squared. And that will be h bar G over c, same base. When you're multiplying the base, you add the power. So that would be c to the power of 5. And that would be the Planck time. So what we could do is obviously work that out. We'll work the Planck time out and see what that value would that be. Again, use a calculator for the values of this Planck constant. A universal constant. So these are universal constant. And I want to write that to be root fraction key, and shift 7, universal constant 1, h bar 2 times, I need to put G there, so I need to go back and do the shift constant 1, and this is 7 for the G, and bring the arrow key down, do the shift 7, 1, 3 for the speed of light in vacuum, but I want to have it to power 5, so I need to press that and put 5 in the little square box and press equals. So the Planck time is 5.4039 times 10 to the power minus 44 seconds. This is the time it takes for light to travel the Planck length. And so this will all happen in the black hole when that's just happened, when the black hole will be formed. We know what Planck mass is, we know what Planck time is, and we know what Planck length is. There is one more thing, so just remind ourselves what is Planck time again, which is that one. Planck length is this one, so let's use a different pen here, LP, which is root, yes? So Planck length is h bar big G over c cube. That's Planck length. What about Planck mass, which is done earlier? That's Planck length. Planck mass, that's MP, will be equal to, and that was h bar c over big G root. So that is Planck mass, and we said that was 22 microgram. And the Planck length was 1.616 times 10 to the power minus 35 meters. Very, very small. Now, the important one that is left to uncover is the Planck temperature. So let's find the Planck temperature. So we're looking for the Planck temperature. To find the Planck temperature, we would be using the ideal gas equation, which is PV as pressure times volume equals to N, number of molecules, times the Boltzmann constant, which is relating the kinetic energy of the particle to the temperature of the gas, and the temperature. So I'm using theta as temperature here because I've used capital T for time. So that will be the temperature, Boltzmann constant, and the number of molecules in the gas. V is the volume and P is the pressure. And in this situation, pressure times volume is energy. That same unit is energy, so that's energy. And therefore, energy will be equal to N kB times temperature. But the N is a constant. We don't need that one because it's just a number of particles in the system. So what we need is to just use E equals to kB times the temperature. So the temperature here this is theta, by the way. That's a Greek letter for temperature, theta. That's a Greek letter. And this is Planck temperature, which is the energy over the Boltzmann constant. And so I can rewrite this in a way by saying that the Planck temperature is E times 1 over Boltzmann constant. So Kb is the Boltzmann constant and N is the number of particles in the system. But what is E? We found out earlier that we said that E is h bar c over r, but the r is LP, the Planck length. And so we can write the Planck temperature as h bar c over LP times 1 over Boltzmann constant. But I need to replace the LP here. So I could say 1 over LP times H bar C over Boltzmann constant. I know what LP is. LP, we just written that down, is root H bar, G over C cube. So 1 over that. So what I could do is write the temperature, Planck temperature to be 1 over 1, because 1 over 1 is 1, so that one. And the LP is this. So I'm going to write it as the root H bar G over C cube times, of course, the H bar C over KB. So you can see I'm trying to simplify this to make it look. That 1 is 1 over 1. 1 over 1 is 1. So I'm creating a fraction and a division in the middle. You know what happens when you divide in fraction by fraction. So Planck temperature will be 1 over 1 divided by root H bar G over root C3. So I'm using indices here for sorts, and then obviously times it by the H bar C over Boltzmann constant. And these I can flip this. So 1 over 1 times root C cube over root HG. So what I've done is obviously when you fraction divided by fraction, you always invert this one and turn the divide into times, which is that one, and then rewrite it. And then times the HC over KB. So now 1 over 1 is just 1. So that'll be equal. So I need to change this. I need to put this into there. I need to put this into there. So I need to turn this into roots. So that'll be root C cube over root HG times root of H bar squared C squared over root of KB squared. So I then put all into it, because root of that is H, root of that H bar, root of C squared is C, root of KB squared is KB. And so I can put these together. So that'll be root, let's use the whole thing, C cube, C squared, H bar squared over H bar G KB squared. And that will be equal to C squared, C cube, C squared is C to the power 5, H bar, because that one H cancels another H, over G KB squared. Planck. So the Planck temperature is finally root of H bar, I like to write the H bar first, C to the power 5 over KB squared, capital G. And what's that value if we to calculate it? So that's the Planck temperature. So that's temperature that will form in the black hole. That temperature will be massive. So let's see if it's true. Alright, so turn that on. We want the root and fraction key inside the H bar, the universal constant, number 2 times speed of light in vacuum, shift 7, 1. Speed of light in vacuum will be 3, but I want to put it to power 5. Press that and then put 5, arrow key down. We want the Boltzmann constant to power 2. So shift 7. Boltzmann constant will be physical chemist. Let's look at that one. 4. And if you look carefully, that must be number 4, K. That's Boltzmann constant. So press 4. You want to square that. That's squared. And then we want to times it by the G, universal constant, and shift 7, 1, and big G, 7. Now, so press equals, and that gives 1.42 times 10 to the power 32 Kelvin. Now that's super hot, because the energy is so high. So those are the derivation for the Planck units, Planck temperature, one of them. There are 4 of them. So now let's write down these 4 Planck units that we've just derived. So the Planck units that we've just derived are Planck units. So the first one was Planck length, and that is LP equals to root for the Planck length, H bar G over C cube. And then we did the Planck time, and that is TP. And for Planck time, we came to conclusion that it is H bar big G over C to the power 5. Then we went on to define the Planck mass and the mass, so that's MP. And the Planck mass was the root, or the Planck mass is H bar C over G. And finally, we did the Planck temperature. So that's the temperature. And so that's theta P equals to, and we get root, and that is h bar c to power 5 over Boltzmann constant squared big G. And the value for Planck length is 1.616 times 10 to power minus meters, and the value for Planck time is 5.39 times 10 to power minus 44 seconds. And for Planck mass, which is 2.18 times 10 to power minus 8 kilogram, and that is 2.2 microgram, and the Planck temperature is 1.416 times 10 to power 32 Kelvin. And this is where, as we said, that the black hole will be forming, because the mass in there will be so dense and the space is too small. Nothing will comes out of there. Therefore, we don't get any information from the black hole because no information is coming out. And light can't even escape it. That's why it's black. Even though, if you see a black hole, it's actually things are going into a black hole, and therefore you can see those energies going in, but not energy coming out. So you will see light in black hole, even though the lights you're seeing are the ones going in rather than lights coming out. Alright, cool. So that was the derivation for the Planck unit without using the dimension analysis. The next derivation for Planck unit is to use the dimension analysis to derive the same thing. So that's the next step.